All right. Before we actually get started, I just want to thank everyone for their thoughts about towards my son at the beginning of class day. That was definitely very appreciated. Last week was a crazy week. If you didn't hear, everything's fine. So we survived. But thank you for your thoughts. I really appreciate it. He's very much okay, and he's back to his wonderful, happy self again. Poor guy. He's allergic to so many things, and most people would be just absolutely miserable and hating life, but it just kind of shows quite instantly his personality. He's just such a happy guy. Yeah, he's a nice guy. Oh, I changed my password. Does anyone else have that common experience, like when you guys probably don't write checks all that often? The generation of writing checks is on your way out, right? But like when the calendar changes to the next year, you keep writing the year, the previous year, like on your checks and your time. I do the exact same thing with passwords, right? I often forget what password I'm currently using. Anyways, okay. So let's just talk real fast about what we're going to be doing today, because we have some fun things. We're going to kind of change gears to a certain degree. We're going to start having some fun. So today, we're going to start our process of really understanding the dynamic simulation tools inside of Modo. Now, up until today, everything's been keyframe animated. However, with the simulation tools, now we're going to be creating a whole series of conditions, and the computer is going to start doing some of the heavy lifting for us. Okay? Now, before we get into this with an intense amount of detail, I think it's really important that we all understand that this is not a replacement for our traditional keyframing process, right? Going forward, this is a supplement to this workflow. It doesn't replace, our point being, don't make everything a simulation, okay? I can't tell you how many times I've seen someone try to simulate an animation when it would have just been faster, easier, and the results would have been better if they would have just hand animated it, okay? So there is a time and a place for simulated animations, especially when there's a lot of detail, a lot of minute detail that needs to be captured. As you'll see in the Week 9 module on Canvas, we have two big things that we're going to be discussing this week, and one of them is such a great, wonderful application of simulation because there's a lot of really small, minute movement. Here we go. So we're going to be making a brick wall and then smashing that brick wall with a wrecking ball today. That's the goal, okay? That's what you guys are going to be building for your homework. Both of our assignments this week, the homework and the lab, are going to be full-blown renders because it's important, to continue cultivating our render skills, okay? So we're going to be rendering everything this week. We'll be setting up some conditions, creating some models, rigging it so that all the dynamic simulation tools will work correctly, and then we'll kind of hit the play button and see what happens, as they say. That's the cool thing about simulations is you set a condition, and then the parameters of your condition will determine how all the simulated pieces move and interact with each other. It's pretty neat. It turns into a wonderful, wonderful, wonderful playground. One that we're going to continue to expand on, so this isn't going to be our only conversation about dynamic simulations. We're going to have another assignment next week that kind of takes everything that we talk about today and we're going to build upon it. I think you guys are going to dig it. It's going to be pretty cool. This is the part of the animation package that a lot of folks have been waiting to get into. So let's jump in and start exploring our dynamic simulation tools inside of Modo. As one might imagine, all of our simulation tools are generally going to be in the exact same spot as they were. Here we go. Oh, this is actually Indigo's mask. It's still on the screen. Creepy and weird. If you haven't seen Indigo's paper mask, I think she brought it last week. Was that last week? Yeah. It's really kind of cool. This is such a great, and I did not intend to, to do this just on the screen, so I apologize for putting the spotlight firmly on you, Indigo. But this is such a wonderful application of our tool set, right? She's making a Halloween costume, and she wanted to make a paper mask of one of the characters from Hannibal. And, of course, she made a model, did some photogrammetry, as they say, took some photographs, make a model from the photographs. She UV mapped it, very specifically, right? Because she had some experience in making paper masks in the past. So the UV map layout here is really a reflection of where and how she was going to trim and cut the paper to make a true 3D mask of this. And this isn't the final model, because because she then brought it over into Photoshop to do a lot of cleanup and cloning of the textures to make it something that she could actually print out. And I think that's really kind of neat, right? Something that starts in Modo, gets printed out, either not in a 3D printer, but a regular printer, right? In which she cut out, made tabs, glued and taped all the stuff together, and made something that was pretty cool. So I like that. That's good outside the box thinking, right? It kind of speaks almost instantly to the power of our tool set. I love witnessing really creative applications of this stuff. It's kind of inspiring. Anywho, let's jump in and start looking at what we're going to be using this week as we explore dynamic simulations. So if you've been hating the setup environment, well, sorry, we're going to be living in the setup world for a little bit longer, okay? The setup world gives us home to all of our rigging tools, but they also are the home to all of our simulation tools, okay? I think maybe the best way to start the process of understanding how to work with the sim tools is to really just kind of recreate the classic bouncing ball animation, right? However, we're not going to hand animate the bouncing ball. We're going to ask the computer, based on the conditions that we establish, to bounce the ball for us. Maybe even down a flight of stairs or something fun like that, because that'd be cool, right? So let's build a very quick scene so that we have something to play with. Now, much like our traditional rigging system and our understanding of the Modo animation system, we have to kind of have a vision of what's physically going to be moving, because this is a continuation of the item level animation system that we've seen in other capacities, right? So I'm going to have a ball. Maybe I'll just make a ground plane initially. Both of those need to be on their own separate item, okay? So let's go ahead and start fleshing some of this stuff out. I'm in the Setup tab if you're not, and let's just bring open our modeling tools. I'm going to hold down the Shift key and click on my little sphere. Okay, there it is. There's my ball. Mission accomplished. I still have some of my viewport textures enabled, which is why it's all red. And here, I'm actually going to turn that off, because it's going to get a little confusing in here with the ground plane and the ball working together. And then last but not least, if you hold down the Shift key, we can add a two-dimensional plane quickly to our environment as well. Now, our two-dimensional plane is way, way too small. So if I change my selection state over to polygons, I can make this thing much, much bigger. Well, that'll do. And believe it or not, that's it. That's all I'm going to really add and create at the moment. Let me turn my grid off so you guys can see what's going on a little bit easier inside the interface. I didn't. Two separate meshes. Yep, I got a plain mesh item. Two separate meshes, yeah. Because remember, each one of these needs, well, the reason each one of these need to be on their own item is because Modo is an item animation system, right? I want to animate the ball item separately from the plane, so we got to separate them out. So if you look carefully over my item list, this is what I have. Just a sphere, a plane, a directional camera, and a light. Or a camera and a directional light, excuse me. All right, so let me cruise over to item mode here real fast. And I'm going to start moving my little ball up a little bit. Okay? Now, for the remainder of this, we're going to be working inside of item level. So this is something that you just kind of got to get used to working in. Okay? Because the entire animation system is item-based. So if you find yourself selecting polygons, stop, undo, and get it back to a point when, before you selected polygons. A great double check to ensure that the center point for your item has moved with the actual polygons is just to fire off the atom transform tools. If the tool handles show up in the middle of the sphere, life is good. If the tool handles are still down there at the origin, you moved the sphere in polygon mode. Okay? All right. Okay. So where do we find all of our dynamic simulation tools? Well, if you look very carefully over in our toolbar, they're pretty easy to find. Right there, dynamics. It's under the weighting section. Okay, we're going to be looking at these two things over the next couple of weeks. Okay, which is kind of exciting. The particle system inside of Modo is a lot of fun. I think you're going to dig it. But for today, let's hang out in the dynamics tab. Okay. So there's the dynamic system inside of Modo requires us to go in and establish a whole series of tags, okay? We're basically telling a much larger kind of structure that certain items inside of our three-dimensional scene are going to participate with inside of a dynamic simulation. So we have to tag those items, tag the participants with the appropriate rigid body tag over there on the left. So that's the first thing that we need to do. And this often is the source of some confusion because there are a lot of tags. There's the active rigid body tag, compound rigid body, kinematic, static, procedural shatter, which is awesome. We're going to take a look at that here in a minute. Okay. There's a lot of tags in here that we can apply. Which one do we start with? Well, here's the idea. I mean, here's where I always begin. If I want the computer to move something, okay, if I want that object to be influenced by the computer's understanding of gravity, forces, and physics, okay, if I want it to physically move, it's going to be an active rigid body, okay? So it's going to be an active participant in the simulation. It's going to be moving. So which of my two items in my scene should be an active rigid body? The ball. Yeah, the ball is going to be an active rigid body because clearly that's the thing we want to drop and bounce on that ground plane. Okay? So let's go ahead and do that. Select my sphere. Bloop. Click on the active rigid body tag. Now on the surface it doesn't seem like anything's changed. However, if we go over to our item list and explore a little bit more directly here, you can start to see that some new things are showing up. Most importantly, or probably, excuse me, most directly is that solver at the bottom of the item list, okay? This is the math, if you will. This is the brains behind the entire operations. The bullet time physics solver is going to, and it really is called the bullet time physics solver, or the bullet physics solver, excuse me, not bullet time, bullet physics solver, okay? I love the Matrix, by the way. The first Matrix is awesome. So the bullet physics solver is the brains behind this entire thing. I consider it kind of like a global understanding of physics. It's the one item inside of our scene that's ultimately responsible for applying gravity, okay, and establishing the computer's understanding of gravity. Yeah?
How do you add the solver again?
So you just click on the sphere, and then over in the left-hand side of your scene, we want to apply the active rigid body tag to the sphere, okay? And the solver will automatically come along for the ride, okay? Once there is a participant, that solver will get created. Okay, so this is the brains behind the operation. However, if I click on the sphere, we have a new section inside of our properties right here in this dynamic tab, okay? This is going to allow us to go in and define the local parameters that will play and will be influenced by the global application of gravity, okay? So this is where we get to go in and really customize how this particular item is going to participate in the larger dynamic simulation as a whole, okay? We're going to be going in and out of this dynamic properties tab often. The most frustrating thing about dynamic simulations is that there is a ton of tweaking. Okay, small, very minute changes in some of these parameters will have a very big effect on how the computer is going to interpret the movement of that item. Okay, so there's a lot of tweaking. It's the most frustrating thing because then you have like, oh, the density. What happens if it's 1.1? We'll see it, right? You get a lot of direct feedback. You don't have to wait 4 hours for a render, right? It's kind of cool. You get some good understanding pretty quickly as to how these parameters are affecting the animation. On that note, let's kind of preview our animation and get everything moving. So in the dynamic simulation tag, or world, excuse me, this part of our timeline becomes really, really important, okay? These three play buttons that are green are where we need to focus a lot of our energy because this is going to start the dynamic simulation, okay? Now the first one, the hollow kind of play button, this is just going to run the simulation infinitely. You press the button, your sim's just going to go, right? It's not going to honor or respect the time range that you've established in your timeline, okay? So it's just kind of a free play. It's a great way to kind of set up your parameters, test some things out, and kind of making sure that you're going down the right path, okay? we're going to be playing with this one a lot. The second one, this one honors the duration that you've established in the timeline. So you're only going to get sim data for, what, for 120 frames, okay? These two are really previews, okay? They don't save the dynamic simulation information. However, this one starts to save it. The last one's going to physically go through and compute all the dynamic simulations information and include it inside of your Luxology project file if we were to hit the save button, okay? So these two are previews, and then this one, we start locking it down a little bit, okay? We'll come back to that one here in a minute. You'll see the benefit of this one when we do a procedural shatter, because sometimes the math and the processing time to generate some of these simulations is lengthy, okay? Because there's a lot of math and a lot of stuff happening on the back end. Yeah, well, luckily the computer's going to do it for us, right? So you don't have to do the number crunching. Let's just do this. Let's hit the first play button down there, the first green play button, and see what happens. Woo! There it goes, okay? I know, not exactly the most stimulating part of our animation so far, but before I hit the stop button, I want you just to kind of bring to your attention some visual cues that a sim is currently running. This stuff over here, it's so obvious that it's often missed, is a great indicator that the computer is actually simulating something. And specifically, it's telling you what it's doing. It's telling us that there's one non-static rigid body, there's one collision shape, there's one collision object, so it's giving you some stats and some info as to what it's trying to figure out, okay? The other visualization that a sim is currently running are, of course, the background buttons of all the background color of all the buttons is orange, okay? And this is a very subtle thing that they actually just added here recently. If you look at the current time indicator, the playhead, it's yellow, okay? Sometimes people forget, believe it or not, that they've changed some, that a sim is still going, okay? Now I want to stop it, and the moment I stop my sim, you can see that the ball goes back to its original resting location. So it's back, okay? Well, let's give it something to do, because now it's kind of boring, but we've proven just very quickly that gravity is now influencing our animation. That active rigid body is listening to the solver, and that the forces that the solver are applying are being transferred onto the active rigid bodies. All right, let's get that ground plane into the mix a little bit. Now, earlier I mentioned that the active rigid bodies are the things that we want to move, right? What would happen, you think, if I was to what would happen if I made the ground plane an active rigid body? It would drop too, right? Let me show you. So I got the ground plane selected, active rigid body, and if I start the sim again, interesting. However, it does work. Now, there's a reason why it didn't fall. We'll come back to that reason here in a second. But let's play it again. Bloop. Cool, huh? Yes, ma'am.
I did static rigid body for the plane. Is that okay?
Static rigid body is just fine. There's actually, I wouldn't actually make this an active rigid body. And actually, did I hit static on accident? I may have hit static on accident.
Is the only difference between an active rigid body and static rigid body is that check mark, that little box?
It is, but there's a little bit of a difference. It's more. I may have. Let's hit active. Oops. Yeah, for the mesh shape of the plane may be getting in the way. But let's think of it like this. Okay, I got my plane. There we go. All right. Let me go back to my plane here in the dynamics. If I turn off static, okay, now they're both going to stay there because the collision shape is set to plane. Let's do hull. No, it's still going to move. Or not going to move. That's okay because this is actually what we want. The differences between an active rigid body, a kinematic rigid body, and a static rigid body are subtle. Okay? A kinematic rigid body is going to be a participant of our entire dynamic simulation. So it's going to send and receive forces from other objects within inside the scene. What makes the kinematic really kind of cool is that we can keyframe it. Okay? Like for example, and maybe we'll do this here in a second, I can create a cube and then I can keyframe that cube spinning and have other rigid bodies be influenced by that spin. Okay? So kinematic rigid bodies can be keyframed. Okay? A static rigid body, it's not going to be keyframed at all. It is really just a static item inside this three-dimensional scene that's never going to move, right? We just like the ground plane. Okay? It's never going to move. We don't want it to do a single thing. We just want it to sit there and receive, information. Okay? We don't want to have it start going someplace else and fall as well. Now, believe it or not, the way that the developers did this is actually pretty cool, because it doesn't really matter when or what, which one of these we establish when we click on it, because we can go back into the dynamic properties of any participant of our sim and change its type just up here. Okay, so if you mess up, it's not the beginning at the end of the world. We can just go up here and say, okay, I don't want it to be a rigid. Okay, soft bodies and curves will come later, but maybe I want it to be kinematic, so I can animate it, right? And I can make it static, and it's non-animatable, but it will be a participant inside of our scene. Let's make a kinematic one. Before we go any further, let's just have some fun with this, okay? Let's make, I want to make another cube. And then in polygon mode on that cube, I'm just going to make it a little bit smaller. I'm going to make kind of a paddle. There we go. And then in item mode, I'll move it up some. Let's move it up a lot. I'll move my sphere up too. There we go. All right, and let's rotate. I want to animate the rotation of this guy here. Let's do it along the Z, rotation Z, and over the course of 120 frames. Oops. Excuse me, I hit the wrong button. On frame 120, I want it to be 360 degrees. There we go. Now you're probably saying, Pat, that's not a very good animation. Okay. That'll do. Okay, I want to be a dork here because I can be a dork. Call this paddle. I'll show you, this is a great trick, by the way. If you have a repeating animation, like I want that little center paddle just to kind of spin indefinitely, but I don't want to have more than 2 keyframes because more keyframes, more problems, right? So I'm going to go in and start adjusting the graph editor a little bit for those keyframes. This is kind of a cool power user trick. I got to apologize for the projector. It's having a bad week. Let's do this. Let's go into the graph editor real fast. All right, so here is the graph for the rotation of my little cube thing here. Okay, I'm going to change its slope to linear in and out. So now we don't get any easing, but that's way too slow. I want it to be moving a little bit faster, but I don't know what the value is, and I really don't care what the value is. I just want to go in and start establishing the speed. Okay. Now the graph editor, by bringing the keyframes closer, we're doing what? Making it faster. We're speeding up the animation. Now the computer has less time to transition between those two values. Okay. That's cool. So I'm just looking at speed here. I'm not looking at timing. I'm just looking at speed. Yeah, that's a little bit there. Okay. However, with my 2 keyframes inside of my graph editor, what's going to happen when my playhead gets to, what is that, frame 52 or something? What's going to happen? It's going to stop moving. I don't want it to stop moving. I just want it to kind of spin infinitely, but I don't want to have a zillion keyframes, and I really don't want to have a keyframed value on that second keyframe higher than 360, because then that just makes the math really tough. So here's my trick. I'm going to create a post behavior. That's what these things are, and it's not labeled really great. if the developers are listening, this is a great thing, low-hanging fruit to change. This should say behavior, pre-behavior, post-behavior. So the first one's the pre-behavior, the behavior that happens before frame 0. Yes, ma'am? So I'm actually in the animation layout. Yeah. I know there's a keyboard shortcut to bring open the graph editor, but for the life of me, I can't remember it off the top of my head.
There was actually a small little button you can press that pulls up the graph editor in the setup tab.
Oh, really?
Yeah. Go to setup, go all the way down, and it's right by audio.
It's right in front of me. Boy, if it was a snake, it would have bit me right there. Goes to show you that sometimes you just get used to doing one thing and you forget that there's... You are absolutely... It's down here. Another thing that the developer should fix, that's kind of... Why would they change the layout? I don't understand that. That doesn't make sense to me. However, that's 6 to 1, half a dozen to another. What I want to do is change the post behavior. I want it to repeat that this function curve indefinitely. Okay? So if we change our post behavior to repeat, that's not what I was after, because when it repeats it, it actually repeats the entire keyed value, and you can see that your graph starts to look like that, which isn't what I want, right? I don't want the animation to start over. If we play it now, when it gets to frame 50-something, well, in this particular situation, since I keyed it perfectly, it's seamless. However, this is what I actually want. I don't want my animation to be, or my post behavior to be set to repeat. I want it to be offset repeat. Okay? And then that way, it'll just keep rotating infinitely. And what this frees me to do is just mess around with these 2 keyframes to figure out the repeat cycle itself on the animation. So now I'm free to go in and say, oh, that was a little too slow. I can just change that keyframe and get a different look. That's Pat's power user trick of the day. Those post behaviors are pretty fantastic. I've done that 1,000 times, and they're wonderful, especially for purpose-built repeating animations like this. All right, now that we have some keyframe data on that cube, let's go back to our dynamic tools and make it a kinematic rigid body. If we play our timeline, awesome. Our little cube is moving, but what isn't moving? The sphere, the ball. The ball isn't moving at all, right? Okay. Now this is where a lot of folks get really confused and they go, Pat, WTF? I hit the green button and nothing happens, right? Hit that first green. If you're following along and you've built a little repeating little paddle as I have, you go, why is it not moving? Yeah. It's still, yeah, mine did the same thing. It still understands and recognizes that it's a participant of the dynamic simulation, but that's not what I want at all, right? I want it to be kind of, flipped, okay? I want that paddle to continue influencing the ball. And that has everything to do with the timeline. Remember, on that kinematic rigid body, we animated it. And its animation values for its rotation z is coming from keyframes that are currently placed on the timeline, okay? The first sim button down here doesn't honor the timeline, okay? The second one does, though, okay? So if you stopped your sim, or I got to stop my sim, and hit that second button, bloop, there it goes. It's kind of satisfying, isn't it? Boop, there it goes. Cool.
If the ball goes through the paddle, does it need to be an active rigid body paddle?
This is going to be a kinematic rigid body.
So I got that
Ah,
part.
okay. Stop it. The middle one. No, get out of settings. Yeah. There we go. Yeah. That middle button is going to honor any keyframed value that's currently sitting on the timeline on a kinematic rigid body.
I got this moving.
Good?
Well, I got this moving.
Yep.
Just that. How do you got the ball?
Hit the middle button. The middle green one. Ah, did you make it a kinematic rigid body?
You mean the spear?
The spinner, yeah.
I don't think.
No, it doesn't look like it. Go ahead and add kinematic rigid body to the dynamic tag, and that will get you what you're after. Yes, ma'am.
My ball is kind of has a mind of its own now. It's kind of.
Oh yeah, that's fun, isn't it? I don't know. Yeah, I really don't know. We can look at some of the parameters here in a second together as a class, and maybe we can figure it out. It could be the collision shape, which is often the culprit. Yeah. No, we're going to talk about soft-bodied objects. I was going to talk about it next week, but the soft-bodied stuff is easy to set up because it's just a different tag. It's very difficult to control. I'd say the soft-bodied stuff is probably a weakness inside of Moto right now. It doesn't have the best control mechanism to give you predictable results.
Right, I assigned a soft body to my plane that just shot up and bounced the ball.
Exactly. Yeah, soft bodies, I think, require the most tweaking. And yeah, it's an area of improvement for sure.
What's its application, like fabrics or?
Yeah, exactly. Basically anything that's, you know, kind of organic. All right. So this is starting to look pretty good. So really inside of our scene right now, we have three very, very different participants of our rigid body simulation, right? We have the sphere, which is an active, the paddle, that's a kinematic, and the kinematic's been keyframed. In the ground plane, really that's going to be a static, okay? Because we don't want it to move at all inside of our simulation. Now let's pretend we mess up, or we decide that we don't want to have one of these items to be evaluated by the solver, and we want to remove that simulation tab from the item itself. Has anyone discovered and stumbled upon how we can remove that dynamic tag from an item? I'm going to do my little paddle guy here in the center. If you return to your commands on the left-hand side, hold down the Shift key. Check it out. Shift, yeah. It's going to remove the dynamics from, yeah, any of them works. So you have half a dozen options there. Yep. Yeah, the Shift key will allow you to go in and remove the dynamic properties of any item. Cool, huh? All right. So now I can just remove dynamics from my little paddle thing, and you can see pretty quickly now, ball goes right through it. Okay, completely ignored by the dynamic simulation. Okay, let's get it back in action here. Kinematic rigid body. Boink. All right. So now that we have a little bit of experience working with the active rigid bodies or the different rigid bodies inside of our scene, let's go in and start changing the parameters of our simulation a little bit to get a different result. Okay, and I want to focus all of my energy on the ball initially, and then maybe we can go back in and adjust the paddle on the ground to start having some fun with all this. Okay, let's select the ball. There we go. Excellent. And then let's examine its dynamic properties. Now there are a couple things in here that we want to start with. First and foremost, collision shape. This is usually a good place to begin your analysis, and almost like an investigation. If you're not getting the result that you think you should be getting, go over here and look at the collision shape. Okay? Imagine that the computer, well, we can actually show it if you'd like. The computer is actually creating a rigid body cage around your item, okay? That matches the shape that we've set here. Now, at the moment, it's a little bit kind of weird because polygonally, the structure of the item that's an active rigid body is a sphere, and the default shape is a sphere, so we're not going to see too much of a difference. However, watch this. If we change the shape from sphere to like box, okay, let's see how that one, and I don't know what this is going to look like. Let's see how that one change influences our animation. Not too much. Still rolls. Let's try hull. Yeah, now it doesn't rotate as much. If you look on mine, it's not rotating as much. Okay, does anyone know what a hull is? The hull of an object. This is something that happens in all items, by the way. So if you had like a character, for example, standing at the T-pose, the computer is going to approximate the total volume of that character. And the total volume is going to be drawn as a hull, which is really kind of like a glorified rectangle, a glorified cube. The size of the character is going to determine the proportions of that cube. When it's set to hull, the evaluation of this active rigid body to the system is very fast. It's very efficient. When you have a whole bunch of parts and pieces, believe it or not, we need to look at ways to make it easier for the computer to manage all this info, because it gets, whoops, projector's on the fritz. It gets pretty intense pretty quickly. Once we start doing the procedural shatter, perhaps you'll see the intensity of the simulation come into the surface. Okay, let's stop my animation here for a moment. The ones that are really expensive is mesh. Okay, because then the computer is going to go through and create a rigid body surface for each polygon on the geometry itself. As one might imagine, if you have a really intense piece of geometry, this is going to slow down your computation time. However, the accuracy is going to skyrocket, right? Absolutely going to skyrocket. We're going to get the most accurate results, but unfortunately it comes at a computational process kind of timeline. And then plane, let's just do plane. I'm curious what the results are going to be. I have no idea. It doesn't even fall as plane. Hey, let's kind of preview what specifically the computer is doing, because there's actually, like I said at the beginning of class today, this requires a lot of tweaking, and at times turning on the debug mode on the solver will give us some direct feedback as to what the computer is actually doing. So just check it out. I've gone ahead and selected the solver in the item list itself. And then down in the Properties tab, the Visualize section is going to be where we're going to hang out. Visualize. And I'm just going to turn on Debug, Locators, and Constraints. So let's just see what that gives us. Now, you're not going to see any of this debug visualization until I start the sim. Bloop. Now we can see exactly how the computer's almost kind of breaking down and constructing all the different players, if you will, of our dynamic simulation. You can see the plane shape for my sphere. Yeah, infinitely just a gigantic plane. Let's see, I'm going to stop my sim. Let's go to the sphere and return to its dynamic properties. We'll change the collision shape back to sphere. And if we run the sim again, yeah, now you can actually see that little white outline. That's the collision shape being communicated to us. Okay. Well, you're not going to see until you hit the play button. Hit the O key on your keyboard. Turn on Show Locators. There they are. Which part? The debug? The debug. It's just a visualization. I'll stop the sim. It happens at the solver item. And then I just turned on debug, constraints, and locators.
So my sphere is awfully light. Doesn't seem to be dropping with any kind of...
Hang out. That's next.
Okay.
Yep. We're going to figure out that stuff next. While we're here, this is actually kind of cool. Gravity. Negative 9.81. Okay, this is the actual, I forget the unit of measurement off the top of my head, but this is the actual influence of gravity here on planet Earth. So the computer's doing a pretty good job, or as accurate of a job as it can, as its science allows, to simulate how gravity is working here on good old planet Earth. We can change this. So if we want our objects to be influenced a little bit less by gravity, by putting this to a value that's closer to 0, we're going to reduce the impact of gravity on our dynamic objects. Generally speaking, though, you don't need to touch it. Yeah. Okay. I'm going to turn off my debug real fast just so I can get a little bit more of a clearer understanding. Bloop. Okay. All right. Let's go back to my sphere and examine the more important parts of its dynamic properties. And there's really three that we need to focus on the most, okay? Bounce, friction, and stickiness, okay? Bounce, as one might imagine, this is going to determine its kind of, I don't know, bouncy properties, how bouncy it is. Is it a steel ball or is it a rubber ball, right? By increasing the percentage, we're making that object more bouncy, okay? More elastic, if you will. The default percentage is 35. However, let's just see what this looks like. Let's put it at 100%. I really don't know what this is going to look like. It could get just bounced off. Boonk. Yeah, earlier, excuse me, at a value of 35, my ball was hitting my paddle, and then it was landing here and then rotating. Now it's being, because its surface is a little bit more elastic, like rubber, it's accepting the force from the paddle differently. And I think that's an important thing that we have to remember as we're going through these dynamic simulations, is that all of the items that are active participants are transferring forces to and from each other, just like physics are doing, right? So if I wanted to make this really, really bouncy, okay, maybe I increase the bounciness of the paddle, and we can see what happens, right? So you have to, everything is influencing everything, right? These forces are being passed from one item to another. So if we're looking to achieve something, we really kind of have to do it from a holistic perspective. Okay. The other thing that we can do on the sphere, or on all active rigid bodies, is increase the friction or decrease the friction. And this is a good place to begin too, especially if you're trying to make the sphere like a rubber ball, okay? In my imagination, this is like how gritty, like kind of like a sandpaper effect on top of our objects. So in my imagination, there's a gigantic piece of sandpaper wrapped around my dynamic objects, okay? If we increase this, we're making it more kind of sticky, okay? We're making the sandpaper almost like rougher, all right? Because have you guys ever done any like woodworking or messing with the sandpaper before? The lower grit sandpaper, like grit like 60, it's pretty raw, right? It's pretty abrasive, okay? Very coarse, yeah. And then you get into the higher grits, like 300 or 400, and it's almost butter smooth, right? Okay. In my imagination, that's kind of what we're establishing here with the fricknish. Fricknish? That's what happens when you try to say friction and stickiness at the same time. You get fricknish. When we work with the friction percentage. Let's just turn it up to 100. So now it's very coarse, and it should be, well, it's bouncing off. Let's do this. Let's put the bounciness down to 0. Hit play, see what we get. Kind of what we had before. Okay. Yes, sir.
So I don't have bouncy, the bounce.
Are you in your dynamic properties tab?
Yeah.
What type of rigid body is this?
I can't remember.
Okay. Let's go into, it's a soft body. We don't want soft body. We want it to be rigid.
Ew.
That was our problem.
Yep. Thank you.
Rigid, not soft body, rigid. Okay. So this is, yeah.
I'm not sure if this is an issue or not, but
Okay.
yours kind of bounces off your plane.
Yep.
Mine stays along the origin.
Right.
there.
Let's do this. So the question was, mine kind of drops. If you look at my ball, it drops, gets hit by the paddle, rolls on the plane, and then falls off the plane as if it's going off the edge of a waterfall, right? You can see it, boop, and there it goes. Woo, right? It's not happening on ROMs, so the first thing that I would look is the collision shape, okay? Let's look at the collision shape for my plane, okay? Mine's set to hull, so it's looking at the total volume that this thing is taking inside of our scene. If I was to change it to plane, this is probably going to do what you had. It's going to roll forever, Yeah, it's an infinite plane.
Does Moto kind of guess what shape it's working
It's
with?
going to guess, yeah. And unfortunately, sometimes it guesses incorrectly. Yeah.
It's having that same problem.
Yeah. The collision shape is the first thing that I check when I start troubleshooting problems. I got to see what the computer assigned. The ones that I usually kind of hang out with are hull, mesh, if I really want accurate collisions, and those kind of do the ticket, do the job for the most part.
I mean, plane's great for ground, right?
It is. It's, I mean, in a situation, if we wanted just to roll infinitely, then this is it. Yep. All right. I want to change mine back to hull. And then, oops, wrong button. There it goes. So here's what I want to see if I can attempt. And this is going to be an experiment. I want to see if I can make the ball hit the ground and then just stick to the ground as if it was just glued to the surface. Okay? Now, let's return to the ball for a second and look at its dynamic properties. All right, so it's not bouncy. It's got a high amount of friction on it. Stickiness we'll come back to here in a second. That actually speaks to the relationship that this object is going to have with another object. Talk about that here in a minute. But let's go to the ground plane and look at its dynamic properties. So I just selected my ground plane, and you can see that we have the exact same properties. Now, if I wanted the ground plane to really grab onto the ball and stop it from moving, perhaps what should we change some of our values to? High friction and low what? Low bouncy, right? We don't want it to, to bounce off. We want it to grab the ball. Let's see what we get. Turn off our bounce, turn on our friction. Let's see what we get now. Kind of the same, okay? Let's do this. Maybe I have it backwards. Maybe I should put friction down to 0. Maybe sometimes, nope. I thought I was right. Let's overdrive. We can overdrive these amounts too. Let's put friction to 300. See what we get. Let's do the same thing for the sphere. Yeah. Let's do this. And this kind of speaks to the recipe that we have to craft, okay? Another player in this is the weight of our objects, okay? The forces that are being transferred may be too high given the weight of the object that we're working with.
Do you have to select the plane, right?
Yep.
But you are in the
I'm on the ball. I have the ball selected right now.
Okay.
Yep. Because I'm going to increase the mass of my ball. I want to make it heavier, okay? And that's going to influence how these forces are sent to and from each other. Let's do this. So there's a couple options. You get local density, local mass. Let's do local mass. How heavy is this? Let's make it a 10-pound ball. 10 lbs. There we go. See how that influences our sim. Yeah, not much. Let's make it a 20 lbs. Oops. 20 lbs, or not lba, pounds. See how that influences things. And we're getting there. Okay. Yeah. I think it's the paddle that's causing so many problems. If you look at it, if you look at my sphere, what isn't it doing anymore? It's not rotating. That's interesting. Let's turn my friction back up to 100% on my ball. Yeah, now it's grabbing. See that one little change? That's interesting. The moment that I increase my friction back to 100% on the ball, bloop. See, it started to rotate. We may be on to something there. Let's do this. Let's put a little bit of friction. See what we get. Oops, I didn't mean to compute. This is where the mad scientists and all of us have to come out a little bit, right? Because sometimes a small change in these values will give you the result that we're after. Yeah, you got it. Yeah. High friction is like sandpaper. Low friction is like a sheet of ice or metal, something very smooth. When the friction's off, it's not going to be influenced at all by the surface.
7,000. Friction doesn't stop at all.
Yeah. Let's see. Let's go into the paddle. Maybe we can start changing some of this with the paddle. Maybe it's just too bouncy on the paddle. We're getting there on mine. Yeah. Let's do this. Let's put the stickiness of the paddle up to 10 newtons. See what that does. Yeah, I didn't think it was going to have too much of an effect. But this is the relationship that you have to go through. It's maddening at times because you have to, sometimes small movements have a big impact on the objects in their inner scene. Okay.
There we go. Stickiness of the ball.
What did you turn yours up to?
I did 20, and it immediately stops.
I'll put mine up to 20 and see if we get the same. Oh yeah, look at that. That is awesome.
It's a Velcro ball.
It's a Velcro ball now. Yep. I like it. Maybe I had the stickiness. That's what I'm going to see if I can do here. Let's see. I'm on the ball. Let's turn the stickiness off on the ball. On the paddle itself, let's turn the stickiness off. But on the plane, let's put the stickiness to 20, and maybe that will grab it a little bit more directly. Kinda. Let's put it at 100. Let's experiment. And it's slowing it down, but let's give the ball a little bit of stickiness too. See if that changes the parameters enough. There it is. Yep. It's like rolling through the mud now. Bloop. Although I did much rather like it having it stuck to the paddle and then just kind of hung out on the paddle. What that stickiness does, and this is my understanding of the stickiness, is that it creates a little bit more of a dynamic relationship between two active rigid bodies or just two rigid bodies. What's cool is that we can, of course, make things glue together, but we can also make them fly apart, okay, based off their stickiness, which is cool, right? Because if you have like two things that are stuck together and they're spinning around, if we increase the rate in which they're spinning, eventually their forces are going to break apart from each other, and that's what the stickiness kind of begins to establish for us. It's kind of fun. Awesome.
But it doesn't look like you're like.
Yeah, it's weird. Yeah, it's.
Right?
This is, and I hope that you guys will start to understand what we are making here is an illusion, right? It really is an illusion. You still have to come at it from a traditional animation kind of perspective, in that we need to view the animation in our mind's eye and have a good solid understanding of what it is that we're trying to achieve, and then we'll use these tools to help us achieve that. Okay. If we come at it through the lens of, hey, we're just trying to recreate something that looks real, you're going to get maybe not the result that you think you're going to get. All right, let's have some fun here for a second, and I'm actually going to remove the paddle from my animation, and I'm going to turn off the stickiness on everything. I'm going to increase the friction to 60% on my sphere. We'll turn off my paddle. On my ground plane, stickiness is at 0. Oops, excuse me. So this is, oops. I'm going to, this is, I do this all the time, because I'm so tied to the visibility of a mesh item to determine its influence. Come on, projector. There we go. I turned off the visibility of my paddle. Okay. Did it turn off its influence in the scene? No. Yep. I do that once a day whenever I'm doing collision stuff. You have to physically disable it. You don't have to remove it. Just got to disable it as a member of the solver. There we go. All right, let's get my ball to bounce a little bit. Now, I made it pretty heavy. Yeah, I made my ball, what, 20 pounds? Okay, so this is a pretty heavy ball right now. So let's really make it bouncy. I'll make the ground plane a little bit bouncy too. That way some of these forces start to work together. There we go. What if I increase the bounciness of my ground plane? Boom. There we go. Wonderful. Right there kind of shows the process you have to go through. I've made the ball bouncy. I'm not getting what I want. Well, let's make the ground bouncier. Let's see if that gives me what I want. There's a relationship because these forces are being passed from one item to another, just like they would out here in the real world. This is the hardest part of the bullet physics engine, is understanding that it's working off of a real world understanding of forces, and forces are being passed between all the different items. Okay, so this is looking kind of like what I want it to look like. Okay, let's change the parameters, and just so everyone's on the same page with me, bounce on both is at 60. Oh, excuse me, the sphere is at 100 and the ground plane is at 60. For both of them, the friction is quite low. I want to put the friction to 1% on the ground plane. Yep, that's good. Okay, cool. Let's start changing the parameters here, because there are other options of our dynamic tag that we need to have some good understanding of to get the solution that we're after. Okay, so I'm going to cruise down a little bit. Got my sphere selected, and I want to check out the impulse section. Okay, because this will allow us to give our object a little bit of a push. Okay, in my conditions, I have just the sphere dropping straight down. Well, what if and you saw the result, right? The ball just drops straight down, doesn't really go anywhere. Okay? That's cool, but maybe we give it a little bit of a push at start to change its movement a little bit as it's falling, right? And that's where the impulse section comes in. And I think of it just really like a gentle little nudge. Okay? What if I want my ball to be going that way? Okay? I don't want it to drop perfectly straight down. I want it to be dropped in an arc. Okay? These impulse properties over here will allow us to do that pretty quickly. There's 3 different sections of impulses that we can do. Impulse X, Y, and Z, this is the push, and how much of a push that we're going to do. The impulse position is where we're going to push our object. Okay? I could push it directly from the top, from the side. We'll see this here. I'll do that here in a second. And then torque is fun. Torque is going to be rotation. Let's look at impulse first. So let's do this. I'm going to give it a little bit of a push along the X. Okay? Now, like most things in computers, we have to be very aware of the positive and negative values as they're being passed onto the object inside of the scene. Okay? If I was to do a positive impulse X, so if I change this to like 5, watch very closely which direction inside of our 3-dimensional scene our object, in our case the sphere, is getting pushed to. So 5 newtons. So here's my sphere. Watch direction. Is it going to go left or is it going to go right? Which direction did it go? Did anyone see? It went to the right. Let's like triple it so it's really obvious. I got a 20-pound ball, so I just need a little bit more force. There we go. Let's make it 30 newtons. There it is. Okay? Whoa. There it goes. Okay? Why did it go to the right? Bingo, absolutely. A positive impulse value will push that object towards the positive side of that axis. Okay? So, with that said, which direction is my ball going to be pushed in if I was to put a negative value along impulse X? Left. So if I want it to go left, negative 30 instead of positive 30, woo, goes the other direction. Okay? So the positive and negative sides of the axes is going to be reflected in the value that we put in here. Okay? And you can naturally do multiples of these. Okay? This is what is cool about working in 3D, is I can push it to the right or push it towards the negative x and the positive z simultaneously. Yeah, there's literally nothing I can do, so we'll just have to endure. I apologize. Yeah, let's do it again. There it goes. Now it's kind of going in a diagonal line, which is kind of fun. All right. So that impulse value is going to be established at one time. It's just kind of a big push. It's going to push it in a direction. However, we can begin to change, oops. Let me get back to my dynamic properties. We can change where that push happens, okay? Maybe a little difficult to see in this particular, here's what I'm going to do, just to make sure it's really obvious. I'm going to change my object from a sphere to a box, okay? That way we can see it getting pushed from a corner rather than from the middle of its mass, okay? So bear with me just for 2 seconds. I'm going to get rid of my sphere. No, I don't want to change its name. And I'm going to put a box in there. I'm going to fundamentally do the exact same thing. I'll make it an active rigid body. Oop, my sim's going, which is why. I'll make it an active rigid body. I'll make it quite heavy, 20 lbs's. Let's test it. Okay. The friction to 1, the bounciness to 60. I think that's what, or I had 100% on the sphere. Let's see what we get. There we go. That's cool. All right. The plane is the same. All right. Boom. Okay. All right. So, let's give it a little bit of an impulse. Negative 30. That was plus 30. I meant negative 30. See what it does. That's a little too much. Oh, that's because I'm on local density. I want local mass. I like mass. There we go. That's cool. If you look at what I have, here it is. Hits the ground and starts going. Ah. Now watch what happens when we start changing the impulse position. Okay. Now we're still going to be pushing negative 30 newtons onto my cube, but where that push is going to happen is going to be different. When all of these values are at 0 on impulse position, where are we pushing this box from? Its center point. Okay. What if I wanted to push it along its top corner? Okay. That'd be interesting. Let's see what happens. Yeah, go ahead.
I don't know why my box is spinning.
I don't know why.
The bounce is not high.
Could be the plane.
The bounce is only 10 on the plane.
Okay.
Friction is
Make it turn it all off.
should be
Yeah.
just 0.
Zero it out. See what you get. Stop the sim. See what happens. Whoa. I don't know. That's a good one. Yeah. I really don't know. Give me 2 seconds and maybe we can come and figure it out. All right. Let's change the impulse position for my little cube here and understand pretty quickly how it's going to change. Now, I want to move it, I want to push it along its top corner. Specifically, that's the kind of the corner that I want it to be fired, to be pushed against. So, let's see. Let's put 1 foot up. Oh, that's not Y. Let's put 12 inches up. And then we will also do, I want to do 1 foot over here too. See how that changes it. Yeah. Cool, huh? Before we changed that impulse position, it was falling straight. It wasn't rotating. So now we're pushing it up here.
Do you select the center point to do that? Or
Nope.
do you,
You just kind of. I wish we could use a center point. That'd be
Yeah.
neat. Yeah. You just kind of experiment with the
okay,
values here.
okay.
You're on meters, so you can just do 1 meter by 1 meter, or you can do half a meter. That's going to guarantee it's on that top, half a meter on the X and the Y. Guarantees it's going to be in that top corner. Because a unit primitive cube is 1 meter by 1 meter by 1 meter. So you can get pretty precise with this. I saw a really great application. I'm not sure if it's around anymore. Let's see if it's around. Hopefully YouTube doesn't mind me going to a website. I'm pretty sure I got dinged last week from YouTube because all of a sudden they said, hey, one of your videos has copyrighted content in it. We're not going to allow you to monetize it. And I went, what? It's a live stream. I don't have any. I think it's because I mentioned Star Wars. I just said it. I know, right? Anyways, okay. There used to be a program called Natural Motion by.
Wait, you just said Star Wars again.
I know, right? I'm so done. Let's see if it's still around.
Can't be bad. I mean, like, there's so many people who just start on a regular basis. There's no way they can't.
I know, right?
Can't get money.
Let's see. This used to be a really cool. I think they've changed. I think they're more middleware now. They used to have a product called Endorphin, which was awesome. It was a ragdoll physics engine that allowed you to establish a whole series of forces and apply those forces to your animations. And it was a lot of fun, right? I remember playing around with it in the office for a long time. All the animators were into it because it turned into, let's see how we can torture our little ragdoll, right? Let's like literally put them on the side of a skyscraper model and then like push his back with the force and see how he tumbled and fell and of course splattered on the ground. It was great. It was a lot of fun. I don't know what they're doing now. They're hiring. Maybe I should go get a job with Natural Motion again. Yeah, it's good stuff. Yeah, I don't know what they're doing now. It's been some time since I've looked at the Natural Motions crowd. They're cool. Apparently you can ride scooters and wear goggles in their office, which is,
Sure, they shoot Nerf guns at each other.
I'm sure they do. Right. Anywho, let's get back to it. So the cool thing about these impulses is that, of course, we can move our objects, but we can also twist them at the same time. Okay? I'm going to turn off my impulse position values just so you guys aren't confused as to what's going on. But this torque impulse is rotation torques. Okay? So I want to have, let's do this a little bit, collapse some of these panels. So I want to let's give it a little bit of torque along the y-axis, which should spin my cube like a top. Okay? Let's put it at, I don't know, 30. See what we get. It's way too much, but it is working. Let's put 10 newtons. There we go. Yeah, it's neat. Kind of starts to simulate some cool fun stuff. Yeah.
So you said that we should obviously use these simulations as a supplement to our animations, but
Yeah.
how exactly will we do that? Because it doesn't show up in the play, obviously.
It doesn't show up in the, yeah, so that's a good question, actually. So what Mike was saying is that I hit the play button. Maybe I'm mixing some simulated stuff with some other keyframe stuff. How do I get everything working kind of harmoniously in the same scene?
That's exactly where I'm
Thus enter the role, and let's just do it here. Thus enter the role of the third button. Okay? This is actually going to physically compute and save a cache of your simulation data on the item itself. Okay? Now, I don't have a tremendous amount of data for the computer to figure out, so it's going to go pretty fast. Check it out. We get to establish a range of frames that we want data to be simmed for. Okay? It's going to look at your scene start and scene end values first. Okay? It was literally that fast. There was no calculation in here at all. We didn't even see the progress bar. But now, check it out. My timeline's still active. And I can hit the play button. I can stop it. Okay? And we're on our way.
Nice.
Yeah.
Say you have like, say you want to have like a character getting in a car
Yeah,
Right.
absolutely.
So
Right.
So you assign the root to that spin position, I guess, or like the main controller to.
Yeah, there'd have to be some engineering. I don't know off the top of my
Yeah.
head specifically what's going to be the participant in the sim, but yeah, that's something to figure out for sure.
Okay.
Yeah. Okay. I don't know why either. And this is kind of the challenge of working with dynamic simulations is that the conditions of all of the participants kind of influence each other. Yeah. Oh, so you're doing some really crazy impulsing, right? What if you turn that down to like -1? Yep. Yeah, you're pushing it too much. Here's a good suggestion as you start to go through this process and become a little bit more familiar. Whenever you change something, play your sim. That way you see instantly and you understand the impact of that change to the global kind of result of your scene itself. Okay? If you make a whole bunch of changes, then you're like, oh, what is causing it to do this, right? Make a change, play it. That way you understand exactly where it's going right or where it's going wrong. Andy.
So my ball is looking more like a balloon. It's acting more like a balloon.
So you did a soft-bodied rigid dynamic.
Oh no, I don't think so. It's just sort of floating gently down to the
Oh,
ground.
yeah, I don't know. The bounce properties for your ball is pretty high, as is the density. Let's change the density to local mass instead of local density, because then we get a number in there. Stop your sim.
Okay.
Try it again. Okay. Did you mess around with the solver at all? Go back to solver. No, this is good. Let's go back to your sphere. Oh boy, I really do. Oh, okay. You changed the scale parameters. This needs to be at 100.
Oh.
Yeah, if you want the object to look bigger, you probably should have scaled the polygons instead of the item.
Oh.
Yeah. So the problem that Andy was running into, his ball was dropping as if it was like the Death Star, right? Just so slow that it was almost imperceivable, its movement, right? I'm going to guess, and Andy, tell me if I'm right, did you return the values to 100% on scale?
Yeah.
What happened? Did it work? He scaled his, yeah, did it work? Yeah.
It's spinning way out of control.
Yeah, okay. So what he had done, and this is probably the root of his problem, is that he had scaled his sphere item to like 6,500%, right? Which is going to change the impact of all of these physical properties on the item itself. In the world of animation, we want to try to scale our items very, very infrequently, especially when it comes to forces like a simulation like this. Patty, do you have a question? Yeah, what do you got? Okay.
I don't know what. No, it's
Yeah,
great.
okay. No, that's good. That's expect. It's probably this impulse.
Oh,
Put that to like -10.
10.
Yeah, see what you get.
Okay.
There it goes.
Oh,
Yep,
okay.
yep,
More.
right.
I have a question.
Yeah, sure, go ahead.
So when I run the simulation using these arrows, it runs fine, no problems. If I run it using over here, and I have redone it here, it'll turn into somebody.
Okay, recache your sim.
I did.
Yeah.
It does the same thing.
Yeah, that's interesting. Try this. Go to the top of the screen where it says dynamics. And let's do, there's a clear cache somewhere in here. Where is it? Oh, that's interesting. Yeah, it's not actually saving your simulation cache.
Oh, okay.
Okay, well, let's go back to your sphere. Let's see what's going on.
Sure. Yeah, 'cause everything here, as far as I know, should be fine. And it's showing it here, but it's just not.
It's not saving it correctly, yeah. Let's look at your plane, your floor. Okay. All right, I don't know. I really don't know. Try caching your sim again. See what happens. Down there at the bottom. Okay. End time. Play it now. See what you get. Same thing. Let's turn the debug on and start debugging this.
It was solver.
Yeah. Just hit play. Or, I'm sorry, you got to play the actual sim itself.
Over here.
Yeah. That's interesting, isn't it? Okay, grab your sphere again. Stop it. Let's grab your sphere. Boy, I don't know. I really don't.
All right.
Yeah. That could be it. Yeah, either your cache could have gotten corrupted somehow, perhaps. Yeah, I don't know. I don't know off the top of my head. An equally frustrating moment when working with dynamic simulations. I get that. Sometimes it'll do something and you go, what? Since the conditions of the simulations determine the output of the simulations, you really have to have a strong working knowledge of how all this stuff is working together harmoniously to make the animation. All right. Let's have some fun here. Now this is going to get a little crazy, but it's Friday afternoon, so let's get crazy. And let's really kind of stress the system out, okay? And this is actually kind of neat. I appreciate this. They have something called a procedural shatter. Now I got my cube selected. Let's turn on a procedural shatter. Now if you just
Whatever was on it before.
a little bit, it changes. It's still an active rigid body.
Okay.
If you look at the dynamic tags a little bit, or
It's basically what you assigned to it already.
kind of a little bit, yeah. If you look very carefully at the procedural shatter tag, it's an active rigid body. It still has that bounce, that friction, that density. That density that we saw before, okay? So a lot of the same properties that we were I just can't talk today, that we were seeing earlier. But now, let's break Moto. This is totally going to crash it, probably. There we go. Yeah, that's cool, huh? It paused there for a second because it was trying to figure out how to break it. Yeah, Adrian. Yeah, so this is the original form. Yeah, it needs to keep that original form in order for it to have a reference of how to slice the actual object itself. I think if I remember correctly, you can turn the visibility of the parent object off, yeah, and it'll still do the shatter. Yeah. Doesn't shatter.
It has the little break apart, but then it just doesn't,
Oh.
it just replays.
Why is yours like this? What? Is that a different
that's
one?
something else.
That's something else. Okay. So that actually brings up the next comment. Okay. If we go into the object that is, or if you go into the procedural shatter, there's a couple things in here that you may want to look at. Okay. That's going to influence its ability to break. Okay. Yeah. So Mookie, you may want to get on this too, right? 'Cause it sounds like you're having a similar problem to Indigo. Okay. So the couple things in here that you definitely want to look at. Okay. Max levels. This is going to determine how many times a chunk is broken into. Okay. That's something to experiment with. Pieces per chunk. That's kind of what this is per chunk. Let's if you lower this, put like 6 pieces. Let's play it. Yeah, now it doesn't break as much. They all slide around. If I put this back up to, let's put like 200. See what we get. It's thinking about it. Yeah, this is where the computer can't keep up. Yeah, let's stop it. Oops. Okay. Darn it. Okay.
Is there a way to adjust the uniformity of the?
There's a pattern. Yeah, this impact pattern up there is going to determine the general rules of it.
So
Yeah.
Will uniformity just goodbye?
Crash. Yeah. Uniform is going to try to break up the block or the shape as kind of consistently as it can, but it's not going to kind of impact's going to give you the best results, right? Because then it's actually trying to figure out like the volume, the mass of that volume, and how those forces would naturally try to shatter that mass. It's kind of cool. I'm gonna compute mine. Let's see. Yeah, it's really thinking about it right now. This is very normal, by the way. It's doing a lot of work. A little progress bar should show up here in a second. There it is. That gives you an indicator as to how well of a job it's doing. Let me turn off my cube and play my sim. That's very satisfying.
A locator does not appear in yours when you activate it. And when I do activate it, this locator appears.
Are you in debug
Let's see.
on the solver?
Let's see, is it in the
Go to the
meshes?
solver.
Oh, the solver. I'm
Yeah.
sorry.
And oh no, okay, interesting. Turn off debug. Okay, let's see, and stop your sim for me. Let's take a look at some of your properties. So that's the procedural shatter. No, well, what you're seeing here, the locator in the center, that's the item locator, right? So that's fine. That's normal.
That's fine. Okay.
Which one of your cubes has the shatter? Is it that one?
That one.
That one? Okay.
And everything else is turned off. So
'Kay.
nothing else should be affecting it, I don't think, other than the ground.
Other than the
plane.
ground, yeah. Okay, let's see. Impact,
And all of those match. what you
braking
had.
force. Now, the height of yours is, it's probably the height. Usually, what, 380 millimeters? Let's see what mine is. To render it. It's a playback error. Well, it's not an error. It's just that the computer has thousands of items that it's now managing, and it's just a playback performance thing. If you had a faster computer, it probably wouldn't do that. All right, so my cube is 16 feet 5 inches from the plane. Mookie, this may be the solution to yours too. The height of the cube as it falls, mine's 16 feet up, and I'm getting a good shatter. If it's real close, the force may not be enough to shatter it.
Can't you adjust the force it takes to shatter it though?
There is a parameter in the procedural shatter that will change the force.
Yeah, I changed it down to like 0.1 Newton.
Look what you've done.
Yeah. Two questions. Are we gonna play with like constraints?
It's coming up next. Yeah,
Okay, and also
that's for our lab. The constraints.
particles, are we gonna do
Next
it
week.
Next week.
Next week.
Because I really wanna.
Yeah, that's next week.
I changed it to so now I can see inches and whatnot. How big was yours?
Mine's 16 feet.
16 feet. Mine's inches.
Inches. So yours is only just barely off the ground.
Yeah.
Yeah, it's way up there. Oh, you didn't need to change the position Z, because then it's 16 feet towards. Yeah. Oh yeah, it's way up there. Let's see if it does it now.
I have to make it bigger so I can see.
Yeah, I may have made mine bigger. Nope, yours didn't shatter still. That's interesting.
Bounces.
It bounces real good, but it doesn't shatter.
I don't know why.
Well, that's frustrating. Let's see if we can recreate it. Here, I'll tell you what. Let's take a break for a second, and then we'll come back and we'll start looking at constraints, okay? I think now's a good time for a break. You know?
I did that and it's still not working.
Yeah. Okay. All right. So while you guys were on break, I was kind of playing around with something that's kind of neat. I continued to refine my scene a little bit, and I came up with something that's really kind of neat. And this kind of speaks to the system that we're playing within. So check it out. If I was to play my animation, this is what I get. Yeah, cool, huh? So I start to slow down reality a little bit here, okay? Now the way we do this, so this is kind of cool, because I'm physically slowing down the solver's speed, its understanding of time. And the channel that we do to animate this, on the solver, right here, it's called time scale. That one. That's the only thing that I'm animating. The default value is 100%. I've slowed it down to 10% of its current scale, okay? And this is the result that we get. Okay, I play. You have to compute the animation, right? It's not a real-time thing. So you play it, and it slows it down. And let's ramp it back up. So let's add another keyframe here. And then over the course of, I don't know, 10 frames or so, we'll have it return to its 100% values. Let's see what we get. So now it's going to slow down a little bit, and then as it gets towards the end, it'll speed back up, and all the little shards should be flying back to its original speed again. Let's see what we get. It's kind of a fun way to play around with it. Cool, huh? All done with that time scale channel on the solver itself. We can physically go in and change its interpretation of time. Since that's the hip, cool thing these days, right? Slowing everything down to extents and extremes that are just kind of, for a while it was new and hip, right? And now it just seems done and old, in my opinion. But that's just me. Of course, I'm of, I remember when they first did it in like 300, the movie 300. We're like, whoa, this is cool. 300 was like 20 years ago, guys. Okay? No, I'm joking. Not literally, but. No, let's see. When did 300 come out? That was right around. That's got to be right around the turn of millennium, 99, 2000, right around in there. Yeah.
I have no concept of time. I was perfectly willing to
2006.
2006. Okay. So it's 10 years ago. 10 years ago.
I said about 10 years.
About your 10. Yeah. All right. All right. Let's keep cruising here because a couple of things I want to talk about before I'll let you guys start working on your homework in your lab. Okay, you'll get some time in class today to start working on these. Let's talk about constraints a little bit, and this has everything to do with your Newton's cradle animation that you're going to be making for your lab. Okay, now if you look at the assignment sheet for your Newton's cradle, I've actually given you a really great visualization of the target, what we're here to make. Okay. Here it is. That is the Newton's cradle, okay? And that's what you guys are going to try to make an animation of, using nothing but active rigid bodies and constraints, okay? And the constraints are kind of fun. Bonus points will go to those that can figure out the curves on how to make to make the wires kind of dynamic objects too, but you don't have to do that. Yes, ma'am?
Oh yeah,
No.
is it 0 points?
It's supposed to say 25, not 0 points. That is an executive oversight, as they say. That one's on me. Yeah, no, it's supposed to be 25. So let's talk about how we can go in and create this simple little animation, because it's pretty easy to craft this result. Okay. You can even do something similar to this for your homework, but I'm not sure if you're going to get the exact same result. It's a little bit tricky to kind of set up, but you may be able to figure it out. All right, so here's what I'm going to start off with. I'm going to look at my scene from the front just for a second. I created a new project file, by the way. Turn off my cameras and lights here. And on a new mesh item, I'm just once again going to create a sphere. Okay. Now, I want this sphere to start to rotate. Boop, boop, okay. I want to kind of constrain it to another object that's also a participant of the much larger dynamic system as a whole. Okay. Now it's really easy to do this. Okay. The part that gets tricky for a lot of folks is the part that gets tricky is understanding the starting location for this, okay? So we got to have another locator in the scene. I want to move this. Oh, I turned the visibility of my locators up. Okay. All right. Now, in every sense, this locator is going to be the object that we're going to constrain my little sphere to. So think of this kind of like a hinge, okay, or a the fulcrum, the point in which a pendulum swings around. I think that's called a fulcrum, right? So with that in mind, if this is where my ball is going to swing around, let's actually move it up a little bit, something like this, right? That way the ball will go woo and swing as if he or she is on a pendulum, okay? Now we're, say again?
You added a locator?
I added a locator, right. Because we have to have some item inside the scene that's kind of feeding the dynamic constraint some position information. Because a constraint, much like we know from our rigging systems, is these are item-to-item relationships. Okay, so we have to have a couple items in here. Now we're going to constrain the ball item to the locator item. So I'm selecting the ball first. Hold down the Shift key, grab the locator, and now over here, down towards the bottom, we have a whole series of dynamic constraints, okay? Pinpoint, hinge, slide hinge, and spring. We're going to focus all of our energy on the point constraint, okay? The point constraint. It's a whole lot of fun. Let's physically create it. You can see that the computer has begun to establish a little line in between the two items, okay? Now, if we were to play the dynamic simulation as is, watch what happens. This is kind of fun. Not a single thing. Hold on a sec. I should have gotten something here. Let me compute. Wait, no. My fault.
I don't think we applied any active rigid or...
That's exactly, you're reading my mind. I was like, I missed a step here, and I forgot to tell the computer, oops, let me stop my timeline. I forgot to tell the computer that the ball is going to be an active rigid body. Now, with the ball an active rigid body, I can shift-click on the locator and add the point constraint. Now it should swing like a pendulum. Cool. So make sure the ball is an active rigid body. Okay. Hold down the shift key. Hold down the shift key and grab your locator. There you go. Then point constraint. Excellent. Go ahead and start your sim. Yep. It moves. Yeah. Point. Hinge is a little bit different. Brings up a really great question. If you want some really great understanding of the differences between all these constraints and how to set them up and their application, believe it or not, the documentation for Modo does a really great job of establishing the differences and the application of all of this. Okay.
Where do we apply the point constraint to again?
So between the locator, the ball and the locator.
Select the ball first. And then
Select the ball first, locator second.
Do a position constraint. Are we not doing that?
A dynamic point constraint. So one thing, and I really recommend that everyone spend some time getting comfortable with the Modo documentation. As I've mentioned a couple times before, it is impossible to know everything, right? It really is. However, what we can know, beyond any reasonable doubt, is where to find the information that we're after, okay? Now, the guys and gals down at the Foundry have done a stellar job of creating some really great documentation. If you go to the Help pull-down menu, there it is, local documentation. There's also an online documentation, which will take you to the web and all that, but the local documentation should be identical to the online documentation. It's going to open up a web browser, and here it is, okay? It's pretty great. I like it a lot. This is actually, believe it or not, one of the better docs out there for the entire app. This is a great place to go to really get a good understanding of how the tools work, okay? And I believe it's under the simulation section, you'll find a nice category that talks very directly about all the dynamic constraints, okay? There's even videos. I'm not sure if the videos are in the local one. They're definitely on the online documentation. Topics in this section. Let's see. Yeah, here they are. Here's pin constraint. I'll tell you how to make them all work. They're pretty good. They're pretty good. Check it out. It's a great resource, one that I leverage all the time because, you know, my brain is getting full, okay? It's important that I know where to look to get all the answers. The documentation are a great, great beginning point. Okay. So with that said, this is in every sense, it becomes the foundation for a lot of different movements, okay? And this is pretty cool. I heard someone said, I wish I would have known this for my chain. You're right, okay? I know, right? Looking back at that first assignment, if we had active rigid bodies for all of that, that assignment would have been super easy, right? But, you know, there's a method to my madness. One thing about the point constraint that's really important for you guys to understand and look at is that perhaps I want to have the point of rotation be at the locator. If you look carefully at how the application is drawing the relationship between these two items, in the center, in the midpoint of that line is that big white circle. Of course, when you hit the play button, that big white circle in every sense turns into the point, the location of rotation for our dynamic object. Okay? If you have the point constraint selected, where is it? Hold on a second. There it, or is the body, maybe you have to have the point, transform, maybe you have to go back to the sphere. There's a way to change the midpoint. It's Friday afternoon, my body's getting tired, my brain's getting full. Why am I missing it? Locator. Let's see, maybe, yes you can. Yes you can. Thank you. So you can change that center point. Okay, and I'm just going to change it to kind of right where I want, where I have my locator. Now if I swing it, whee, it's going to swing from that point, which is cool. There used to be, and this may just be a change that I was unaware of, there used to be a value that you got to determine the midpoint, and if it was at 0%, it was all the way to the left. If it was at 100%, it was all the way to the right. This works just the same. So what's cool about constraints, and you can see this pretty easily, you can actually make it breakable. Yes. Okay. Right. No, exactly, because there's real-world forces being applied to all these objects. So we start constraining different spheres of different weights together. We can break them apart. Here, actually, let's actually do what Indigo did, because that's very entertaining. That might illustrate quite wonderfully what we got going on here. So let's see. I'm gonna guess. Let's do this. Yeah, I got it. So Indigo, what did you constrain yours? Are they two spheres constrained together?
I actually just duplicated what I had made without the point, and then I just applied a point to it again, and it did that.
Let's see. Here, I got it. This will be fun. I'm going to create another sphere. Oops. Make my second sphere an active rigid body. Constrain it once again to that exact same object, right? And then for the locator, I'll make it a kinematic rigid body, and then I'll just spin it. I have no idea what this is going to do. Okay, cool. I haven't animated the, let's see, I want to animate it around the z-axis. So over the course of, yeah, it's so much fun. This is where you get to have more fun than you're allowed to have. Okay. Oops. That didn't work, but you can kind of start to see it a little bit. I was hoping it would start to flip it around. But point being is that we now can pass forces to one another pretty quickly. Okay? Let's do this. This will be fun. Bunk. Here, on this second one, let's make it breakable. Yeah. Isn't that cool?
Wait, did it just fall off its constraint?
It did. It break. A constraint can be broken, right? When a certain force is applied to the secondary object, we can break the constraint. Bloop, and there it goes.
Did you have envisioned that it would shatter? Or
Say again?
did you have envisioned that that thing would shatter?
No, it did exactly what I envisioned it would do. Just kind of the constraint was broken. Yeah. I basically just turned it off. Turned off that dynamic constraint when a force was applied to it. Yep. It's pretty cool, huh? So this is really the underpinning of our Newton's cradle. Now the forces, you're going to have to experiment with the correct position of all of these objects and their weight, their dynamic properties, to really try to get the forces to transfer to one another. It's going to be a little bit of a challenge. The big suggestion and hints that I would give you in this process is to really play around with the weight of your object, okay? Think of that little ball like a bowling ball, okay? You got to make it very heavy so the weights are going to be transferred correctly, okay? Because, as an example, if I turn off the breakability of my second point constraint, we saw this in action a minute ago. Bloop. It works, right? It will do it. And make the, let's make the density like 50. See what happens. Oof. Yeah. Local mass. Let's make this 100 lbs, 100 pounds. See how that changes it? Oof. Yeah. Because the second one is so light, it's not stopping it. Let's make this other one local mass 200 lbs. See how that changes the sim? Oof. Ah, interesting, right? So you're going to have to experiment with this a little bit, okay? You have to experiment. That's part of the challenge, okay? If it's not identical, not the end of the world. I just want you guys to have some experience setting up these constraints, making it animate and rendering, okay? Now, at the end of this process, when you're about to render, don't forget, okay, to cache, compute your actual simulation data, okay? In addition, when you, if you're really in love with your sim and it's working perfectly, it's dialed, it's correct, here's something that you could do, okay? Save it, okay? Save all your simulation data. What this is going to produce is a new file, okay? I'm going to put this on the desktop. I'll just call it Pat's sim data. There it is. That's it. That's all your sim data in one file, okay? I almost always do this out of a habit and then load it when I'm ready to render. That way I have kind of a clear, consistent kind of animation throughout the entire pipeline. Yeah?
What's the E-R-N-I?
Ernie. Yeah, it's Ernie. It's Bert and Ernie. It's Bert's best friend.
So you cannot do a sequence of this, another ball, another ball.
Oh, yes, you can. Yeah. No, this, and what's going to be saved in here is the sim data for all the items in your scene. It almost kind of ensures that what you do at, on Friday afternoon is going to be what you see when you open up and load the sim data on Monday, for example. And if it's a sim that takes forever for the computer to compute, you do it once, you save that data, and then you just load it back in that same pull-down menu back in Modo, right? Under Dynamics, you can load that simulation data, yeah, and you're on your way. Yeah?
Do we only use one locator or can we use multiple?
Well, I would probably use multiples. Yeah. Yep.
So this is basically like an introduction to the Newton's cradle, but you mentioned the string part, and I was very curious about that.
Yeah, I'll let you guys figure this out. I'm not expecting everyone to do this, okay? However, if you'd like, okay, this is kind of one of those things that I would encourage you to look at. Make dynamic curves. Yeah, it's good stuff. It's good stuff because curves are a great, great, great tool for us inside of Modo, right? Instead of, like, for example, instead of I saw a great application of this idea for a bowl of spaghetti. Who wants to model the noodles in a bowl of spaghetti? That's right, nobody wants to actually go in and hand model a bowl of spaghetti, right? So what this one artist did is he made a curve, right? Then he duplicated this curve 80 times. I don't know how off the top of my head. He made them all dynamic curves. He dropped it in a bowl that was a static rigid body. They all deformed and moved around like they were supposed to, okay? Model done in about 5 seconds. It's pretty great. Yeah, it's pretty cray-cray. It's pretty neat. Explore it. Look at the documentation. Figure out how this works, okay? I think it's part of the puzzle that we're putting together. It's not expected that you do it, but if you want to kind of start taking it up to the next level, definitely check it out. It's good stuff. Our sim stuff is a tool that extends much further past a regular animation world. I use all the sim stuff, to be honest with you, in my modeling all the time. All the time, right? Do you think I'm going in and hand placing rocks in an environment? No, right? This is the old school trick, right? You craft your environment, you sculpt your environment, you put all your rocks above the environment, set them as active rigid bodies, your environment as a static rigid body. You let them fall, land on the environment, done. No, I'm serious. I'm serious. Like let the because then the rocks are going to naturally roll where the curvature and the topology of the terrain would have them roll to, right?
Or could you have like a mountain and then like break it and then just have everything fall down?
Yeah, why not? I've done this with a jar of actually, this is actually cool. This is a great example of something that I've done recently with the sim tools inside of Modo. Did some motion graphics for GCOM. Some of our promotional stuff. Yeah, this is not anything new. However, okay, all dynamic rigid bodies, yeah. It doesn't stop. Actually, the animation for that is like 30 seconds long. Yeah, it's just like this never-ending stream of GCOM logos falling. And yeah, I was working on this last semester a little bit. Yeah. Yeah, I did something very similar for a clear jar of Legos. Because I wanted to have a clear jar. I wasn't going to hand place every single Lego. Are you kidding me? No way, man, right? I dropped all the Legos in the jar, done, right? The Lego bricks kind of figured out their resting places inside the jar, saved my simulation data, baked it all down, finished. It's pretty great. Yeah. Pretty great. Okay, here's what, let's go back to the assignment sheet for the Newton's Cradle. I'll let you guys start working on that and your homework, okay? All right, so you're going to model this. Keep it real simple, okay? If you don't have a really great, strong modeling tool set, that's okay, right? If you think about it, it's just really a couple cubes stacked on top of each other to make the base. If you wanted to go crazy and make some cylinders to kind of simulate the frame, that's fine too, right? The expectation on the modeling side is going to be very, very low, but I do want you to start going in and building something that kind of starts to suspend disbelief a little bit, okay? And then the big part is going in and establishing all the dynamic properties for the moving items to get it to work, okay? When you're done with this, render it, okay? Let's do a full-blown render. I say in the expectations, a simple environment for your scene is going to be required. The studio environment presets are excellent, okay? For example, if this is my scene, okay? Let's open the render preset browser. Okay, now I'm going to go into my environments, okay? And the studio section is quite wonderful, right? That one right there would be great, or any of them, actually. Yeah, there we go. This is great. This is a great starting point. Okay. If you really wanted to have shadows cast for all this stuff, the shadow catcher will help. You can find the shadow catcher in the meshes section of the environment or the Modo preset library, and it's under the basics folder. There it is. There's the shadow catcher. That will allow you to, yep, there it is. You can see the shadows that are being caught. Okay. It's a great way to just kind of keep the scene light and really rely upon that background image map to kind of fill in the blanks a little bit. Yeah, it's good stuff. You can even go in and turn the diffuse amount down, specular up to like 80, maybe even more than that. Change your roughness down to like 10. We're halfway there. Cool, huh? The total duration for your Newton's cradle, 5 seconds. Okay, so it's going to be a good little render. Okay, good little render. It should be pretty satisfying though. If you get it all working, just kind of want to go blunk, 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 blunk for 5 seconds. It's going to be a whole lot of fun. Okay. If you really, really wanted to kick it up a notch, okay? Now, I'm only going to recommend that you even consider this if you have some render time to burn, okay? If you can commit some time in the lab to rendering, or if you have a schedule over the next week that allows for some long late-night renders. Let's see. In this particular, okay, cool. So my chrome balls are in motion right now. One of the things that will really, really, really take this up a notch is motion blur. Okay, that's going to help. The motion blur that's created by the camera itself will start to physically blur the balls in movement. Okay, and kind of create a realistic reproduction of what a camera would create. Now, adding motion blur is really, really easy. In this version of Modo, they've tucked the camera under the render item. That's what, in the past, it used to be down here in a section just for cameras. Now it's under the little plus sign. And there, yeah, that's where it is now. Okay. If you have your camera selected, and FYI, you can do the exact same thing in the item list. Okay. It's under camera effects. Just turn on motion blur. Okay. The general rule of thought is that you want to have a shutter speed that's twice your frame rate, which is why the default's at 48. Okay. That's kind of the starting point for almost everything when it comes to the shutter speed. If we increase the shutter speed, we're going to decrease the motion blur effect. 48 is a really, really, really good starting point. There has to be a damn good reason for me to increase this past 48. I often don't even look to do it. A lot of folks, they look at this and they go, Pat, you said there's going to be motion blur on this, right? If you look at the actual object in motion, which is this one, it looks the same. That's because in the preview window, we're not previewing motion blur. It's something that you only see upon render. However, if you really would like to, go into the options section of your preview window, and it's in here. It's towards the bottom. There it is, motion blur. If you turn that on, yeah, now we can see that the render camera is starting to blur it out a little bit. This is good stuff. Yes, sir.
Mr. Crandley, how do we record the simulation?
Yes, it's that third button.
This one?
That's the one. Yep, you got it.
All right, thank you.
That's the one. Buyer beware, though, on this motion blur. Okay, this is going to take your render from 10 minutes a frame to 30 minutes a frame pretty quickly. Okay, so 30 minutes is a gross exaggeration. It's not that extreme. Actually, let's just test it real fast. I'm curious. Now, I don't have everything going in here, and I just have 2 chrome spheres. So if I render as is, this is a wicked simple scene, but it should give us a good understanding of how much longer it's going to take. 6.2 seconds with motion blur on. If I go in and turn it off and render, watch it be longer. Yeah, so 0.2 seconds less. That is a percentage increase and decrease by turning on motion blur. But it really makes it look sweet. Yeah.
I get a question about if I want to rotate the ball around, so I have my point here, right, that it's hanging from essentially.
Mm-hmm.
And if I want to rotate it around that point, how would I go about doing that?
So grab the point constraint themselves.
Okay.
Oh, that's the locator. Yep. Now hit the Y key. Oh no, you're doing it.
Yeah.
Yeah, you're good.
That rotates. This doesn't rotate the ball.
Yeah. So the starting position for the ball needs to be up here, and then it will boonk, rotate down.
Okay. So I just need to, I guess, move this.
Move it. Yeah.
Okay. Right.
All right. Since I have your attention, let's just talk real quickly about your homework this week, because your homework is going to be another one of those fun projects. Okay. The Newton's cradle shouldn't take you much more than 45 minutes or an hour to kind of set up and get rendered. However, the brick wall, very different. Okay. The brick wall is going to be a much larger application of these ideas. Okay. Let's talk it through, because sometimes that's the best way to really understand what we need to create. So in order for us to get the wall to smash, how are we going to create the wall? It's multiple cubes. So it's not just one gigantic cube that we're like procedurally shattering. You don't have to do that, and that would kill your performance, by the way. You could do that, but we don't want to, right? It's really one brick, okay, that we then duplicate to create a wall, okay? And then you can figure out the rest, okay? In the past, people have made just one gigantic cube and then the ball is smashed it. No. I want to have each individual brick, moving and flying around inside the scene. It's going to be pretty neat. Make a lot of bricks. Yeah. Yep. Part of the challenge. Yeah, so the question was, how do we stack the bricks perfectly? It takes some experimentation. Yep. Huh? Clone's going to help? Yeah, but even the correct position of the bricks is important. Hint, maybe don't have them perfectly cloned on top of each other. Give them a little bit of breathing room, a little bit of gap in between each vertical row. And when you start the sim, they all should go clunk, right? They should all collapse on top of each other and like physically solidify into a wall. And then the big thing can come in and smash it. Cool, huh? Sound good? Everyone understanding the assignment for the brick wall? Also, make a good render out of it. Spend some time on materials and textures and lighting and environments. This is going to be a fun one that you'll definitely want to keep. And it's so much fun to see a wall get destroyed by this gigantic wrecking ball of a thing, right? Now, the good question, the good challenge would be, could you like model a chain with all these like point constraints? And have like each link of the chain. That'd be an interesting, I don't have the answer to that, but that'd be something fun. That'd be a level of detail that would be neat to see if we can try to simulate. Yeah. Question, I saw a hand go up. Catherine.
It's actually unrelated to brick wall, just something about curiosity. Is it possible, like with dropping the ball onto the box, is it possible to make the box sort of spin?
Oh, yes. Actually, that we're going to talk about soft body dynamics next week.
Okay, because I was trying to mess with the soft body, but it caused the box to also fall. So
Yeah, we have to pin it. The corners of the box are going to have to be basically deactivated from the simulation itself, but all the interior ones we want to be.
So it holds them all in, and so maybe those ones are a different sort of rigid body than the rest of the box?
Yeah, a little bit. Yeah, we'll talk a little bit about that next week.
Okay.
Yep. But you're in the ballpark, as they say.
Yeah, for now.
All right, let's get to work.